let's start with the first research seminar in this academic year. So welcome back. Because of this COVID-19 situation, we decided, at least for now, to organize kind of a mixed seminar. So it will be always available via Zoom, but there will be also live streaming in the lecture room. This is the Velika Predavalnica ENA lecture room. So whatever you prefer, you could join us via Zoom, or you could drop by the Velika Predavalnica ENA and follow the seminar there. Let me also welcome our new PhD students who are among us today. I see that Noemi Matavul is with us on the via Zoom. So the second PhD student is Sara Pia Zemlic. I don't know whether she is in the lecture room or not. And we have another PhD student, Gregory Robson, but he's excused to follow the seminars because he's not in Koper for now, and it's 4 a.m., I guess, 4 a.m. At his home. So that's a good reason to be excused from the seminar. So our first lecturer today is Russ. He will talk about combinatorial shifting via limits of matrix actions. And let me also mention that this Zoom meeting is being recorded. So Russ, I think that you could start now.
Well, thank you for the introduction. Does everyone hear me okay?
I can hear you fine.
It's all right also in VP1? Okay, I'm going to assume that quietness is contentment. Well, thank you for the introduction. Thank you for having me. I want to tell you about some work I was doing. I'm going to mention, I have a fancy setup. I'm using some software called OBS, which is Open Broadcasting System or something like that. And it lets you do some kind of cool stuff, which I'm happy with so far. And let's see if I can make it work. Okay. Right. So combinatorial shifting via limits of matrix actions. Well, I have prepared some materials on the background here. So I want to start by telling you what this combinatorial shifting is. And I think that some of you will have seen this before, but I'm certain that everyone could use to be reminded. So the big picture is that this is a method to simplify a set system while preserving a lot of nice properties you might be interested in by repeatedly replacing large elements with small elements. Okay, and my set system here is going to be a set system on the integers 1 through n. So large and small just means bigger or smaller in the usual order. Okay, so the details of that are as follows. Someone hands you a system of subsets of 1 through n. So system here is just a new synonym for family or collection or set. But as usual, you get tired of thinking about saying set of sets. So you use different words. And if you want to make what you're doing sound serious, maybe you call it a system of subsets instead of a family of subsets. Okay, so you have a system of subsets. And I'll have a bunch of shift operations that I can apply. Sij, where I and j are integers, 1 through n. So what Sij will do is it will look at each subset in the family. And it's going to look for subsets that contain J, but that don't contain I. Okay? And it would like to replace the subset that contains J, but not I, with A minus J union I. So I'm going to take out J and replace it with I. Okay, so something that could happen is that A minus J union I, the thing you get by doing this replacement, is already there. So if it's already there, don't do anything. If it's not already there, go ahead and replace it with this thing which is moved over conceptually sort of to the left. Okay, so here's a small example. I'll take the family of sets 1, 2, 2, 3, 2, 4, and I'll apply S12. So I should say I'm going to be extremely cavalier about writing set braces. So this 1, 2 is representing the set with elements 1, 2, similarly for 2, 3, and 2, 4. And I won't deal with any numbers bigger than 9. Okay, so if I apply S12 to this, then, well, let's see. S12, that contains 2, but it also contains 1, so I'm going to leave it alone, and it just comes through. Now, I look at my 2, 3. Oh, and I messed up my example. Right. I look at 2, 3. I'm going to try to replace that 2 with the 1, and in fact, I can do that. So I will get 1, 3, and similarly with 1, 4. So let me do the example I was intending. Let's see. If I apply S12 on 1, 2, 1, 3, 2, 3, then, well, 1, 2 I leave alone because it's got both. 1, 3 I leave alone because it doesn't have 2. 2, 3, I want to replace that with 1, 2, but I can't because 1, 2 is already there. So that yields exactly the same thing. It doesn't do anything here. Okay. Meanwhile, here's something where it does do things. So the interesting thing about this is that if you repeatedly apply these operations Sij over all I less than j, then it's a theorem that that eventually stabilizes, and you get to a point where none of the operations Sij with I less than j do anything. So you get to what is called a shifted set system. So you apply these combinatorial shift operations repeatedly. When you're done, you can't shift it anymore, so you say it's shifted. Okay, so it's just shifted just means stable under all these Sijs. Okay, so the classical application of this is this theorem of Erdős-Ko-Rado, published in '61. If you have a family of small subsets of 1 through n, so I want to take k element subsets of 1 through n, and I'm interested in them being pairwise intersecting. So that just means that every pair has a non-trivial intersection. Now, if I've got 6 element subsets of 1 through 10, then every pair has to intersect by the pigeonhole principle, and that's boring. So I want k to be less than n over 2, less than or equal to n over 2, so I can potentially have pairs of subsets that do not intersect. Okay, so in that situation, I have to have the size of my family of sets to be at most n-1 choose k-1. Okay, so now this looks a little bit boring or bloodless when you see it like this, but the point is that the biggest family of pairwise intersecting subsets in this situation is the obvious family. You take the family of all subsets containing, say, 1. Okay, that has n-1 choose k-1 sets in it, and it's certainly pairwise intersecting. Okay, so the original proof, so this is a fun theorem because you need a technique to prove it, and sort of any non-trivial technique you apply will work. And there are approximately a gazillion different proofs. The different proofs come in several different families. One of them, the original one, is by combinatorial shifting. So what do? You shift your set system A, so you repeatedly apply these operations. You check that everything up here is preserved under them. It's obvious that shifting preserves the size of the family. It's a little check that it preserves the intersecting property, the pairwise intersecting property, but that's not difficult. And now you check that the theorem holds for a shifted system of sets. And it's much easier to check on a shifted system of sets. It's a simple induction. If you don't have a shifted system of sets, then it's really not so clear. Okay, so these are the background things. So far, I think that everything I've said is something that you at least might have seen in a class. I don't know if you do Erdős-Ko-Rado and discrete math 2 here, but you could do Erdős-Ko-Rado and discrete math 2 or a similar class. So now I'm going to tell you about stuff that you don't know. Now I'm sneakily giving something which is in some sense the second part of a 2-part talk. It's a 2-part talk that I think Andres is the only one that attended already, unless Nina is also in the audience, and I don't think she is. I apologize if I'm forgetting anyone that was there. So I'm going to give you the short version of another talk, which is I have an alternate approach to shifting, which is looks a bit different. So what I want to do is take my set system A, and I'm going to take all the sets, and I'm going to identify them with monomials in the exterior algebra. Over n variables. Okay, so the exterior algebra is a gadget in, I don't know if this is linear algebra or some people might think it's differential equations because this is the algebra of K form, or you might think it's ring theory, but this is the thing to say about this is that it's like the polynomial algebra. On n variables, but I'm going to write a wedge for a product, and it's anti-commutative. So when so it's not commutative, but it's the next best thing. If I take x wedge y, where these are 2 variables, and I reverse the order, then I get a minus sign. So x wedge y is negative y wedge x. And x wedge x is 0. Okay, and this is for variables. Okay, so if you've never seen this before, then, well, I claim you sort of actually have seen this before, because this, a simple example of this is the algebra of formal cross products. Okay, so you take your cross products, you forget that your cross product is a vector, and you just look at it abstractly. You get, well, the cross product is anti-commutative, and if you take a cross of a vector with itself, you always get 0. So this is just an extension of that. Okay, so I'll identify my A with monomials, and I'll identify my script A with a subspace of the k degree part of this algebra. Okay, so I'm going to try to do a lot of examples and not talk about too much theory. So what did I look at before? 1, 2, 2, I don't remember what I had, but let's do 1, 2, 2, 3, 1, 4. This will correspond to the subspace generated by E1 wedge E2, E2 wedge E3, and E1 wedge E4, where I'm calling my variables E1 through En. I'm calling them E1 through En because I can think of them as being standard generators for Cn if I want to think about this more strongly as having some connection with the cross product. Okay, so let me pause in case this is all Hungarian to everyone here, except for István. But Hungarian to István, and István understands Hungarian, so that's good. Okay. Okay. So this property where the product of a variable or a vector in general with itself gives 0 is helpful for this intersecting property, because now A intersects B is non-empty. It turns out if and only if one direction is immediate and the other direction is follows from some kind of universal properties. Let's call this monomial MA up here. So now if and only if MA wedge product MB is 0. All right, because if you have something that occurs in both of them, then that already gives you 0, and 0 times anything is 0. Okay, so so far I've been explaining everything. So now I'm going to use some fancy words. So it turns out that the set of V subspaces of the K part of big lambda Cn satisfying the property that V wedge V is 0. So this is the analog of the pairwise intersecting property. Forms an algebraic variety. Okay. Algebraic variety, I think I just won't tell you what it is because it's not going to be necessary. But the advantage of this is that the Borel Fixed-Point theorem which depending on how you, I don't know if this is from algebraic groups or algebraic geometry. But probably you should think of it as being from both. This gives a fixed point under the action by upper triangular matrices. Okay, so by upper triangular here, I mean I have anything non-zero on the diagonal, I have anything above the diagonal, and I have 0 below the diagonal. Okay, maybe I should say by upper triangular, let's say matrix group. Okay, and this fixed point, it comes from a set system in this sense, and indeed it corresponds to a shifted set system. Okay, so in one step, applying this big kind of mysterious thing, you get a shifted set system. And let's go back and remember a second the idea behind the proof, behind one proof of Erdős-Ko-Rado. You replace A with a shifted system having the same properties, and you check that it holds for a shifted system. So now the one-line sketch that I gave up there replaces this part with the Burrell Fixed-Point theorem. And it's not clear that that's an improvement or not. The big advantage is that this tool might be available in some settings where the combinatorial shifting is not. Okay, so I actually get a little bit stronger theorem here. But well, let's not. Well, okay. So the theorem is that if V is a subspace of lambda k Cn with k less than or equal to n over 2 and V wedge V 0, then the dimension of V is at most n minus 1. Choose k minus 1. Sorry, I'm getting out of the screen here. So this was independently discovered by Scott and Wilmer, and they got their paper to the archive a bit before me, so I'll credit it to them. I'm calling this a theorem, and it's a little advanced, but it's pretty closely equivalent to Erdős-Ko-Rado. So, okay, there's this Burrell fixed-point theorem. Who cares? I'm not going to explain the technicalities. It suggests a couple of questions. One is, what is the relation with this combinatorial shifting. That I have a pretty good answer to. The other is there's a stronger form of this Erdős-Ko-Rado theorem. And let me just say the question for vector subspaces. So let's see, if V is contained in lambda k Cn, and by contained I mean as a subspace. And it has dimension equal to n-1, choose k-1. You know, and V wedge V is 0, and k is actually strictly less than n/2. Let's say, do all elements of V have a common factor? Or perhaps I should does the family of elements of V? Okay, so is there some vector, some sum of variables, linear combination of variables, where it divides every element of V? So the analog for Erdős-Ko-Rado is there in this situation where you're at the have a largest possible set system, is there a element which is contained in every set? The analog for the Erdős-Ko-Rado system is known to have a yes answer. It's known to hold there. I don't know the answer to this question. I think it's a good problem that some enterprising students might like. I do have an answer to the first question, which I think is pretty satisfactory, and I want to tell you about it. Okay, so here's a tool for 2 and an answer for 1. I should mention that there's an alternate answer for 1 by Murray and Hibby, but you probably would like it less. So let's see. I'm going to, well, let's see. I've got these matrix groups like this. I'm going to take specific matrices in these groups and repeatedly apply them, and I'm going to take some limits, which is sort of where this fixed point is going to come from. So I'm going to consider the matrix of the form. It's going to have 1s on the diagonal. It's going to be 0 below the diagonal, and it's going to have a single non-zero entry T above the diagonal, say in position ij. So let's call this Mij of T. So I think to make this work out right, I need to have my matrices act on the right, which is the right way to do it anyways, because, well, right is right. So this is going to be the matrix sending Ej to Ej plus Tei, and fixing the other basis elements. Okay, so this acts on a lot of things. One thing it acts on is this lambda k Cn. Let me build that up. So it acts on Cn, surely, because that's what matrices do. It doesn't have a limit, and that's kind of boring to me. More interesting is it acts on the projective space. PCN. So you can think of this either as the set of one-dimensional subspaces of Cn, or you can, you might have seen this in a class where you do something equivalent. You take all the vectors in Cn and you mod out by the equivalence relation where you identify vectors that differ from each other by a scalar multiple. And I guess you better throw out 0 when you do that. Okay, of course, vectors up to a scalar multiple and one-dimensional subspaces are the same thing, so nothing more to say about that. Here, things get more interesting because this matrix sends EJ to EJ plus TEI, but this is the same up to this equivalence to 1 over T EJ plus EI. And right, so I just divided both sides by the scalar T. And now I can take a limit as T goes to 0, excuse me, as T goes to infinity, this goes to 0 plus EI, also known as EI. And again, that's as T goes to infinity. Okay, so this already gives some somewhat non-trivial behavior. So let's take E2 plus E3, for example. So I'm applying, I'll apply M12 to that. And I'll give you a second to think about it. Your intuition here might be a little different from what happens when you actually start calculating. Well, let's see. So now this fixes this M12 fixes E3, and it does something to E2. So let's see, I get E2 plus TE1, and the E3 comes along for the ride. Now I can divide through by the scalar to get 1 over T E2 plus E1 plus 1 over T E3, and that goes to just E1 as T goes to infinity. Okay, so if you picture the projective space as being a sphere, which, okay, it's a sphere up to identifying antipodal point. Picture it as being a sphere. You've got this plane where you don't use E2 or don't use EJ. That plane is fixed. Everything else here is going to get attracted to E2 or more generally to EJ gradually as T goes to infinity. So the limit point will often be, excuse me, the limit point will often be E1 or EI. Maybe the picture I was describing breaks down a little bit, but I hope it helps slightly. Okay, so this is routine stuff. to build up, it acts on the variety of vector subspaces of Cn. So up here I had the variety of one-dimensional subspaces of Cn. I said the sets, but okay, variety for us means set, except Russ is saying variety for some reason. So you take the action on, well, you take the action up here, but now you also can do some row reduction. So the action is as for P of Cn on the basis elements, or whatever, vector subspace is V, let's say, on basis elements of V. And we can also row reduce. Okay, so that's a little bit vague. I think what would be helpful to get a flavor for this is an example more than any kind of, certainly more than any kind of proof. So let's take V to be generated by E2 plus E3 and E1, say. So, and I'm going to take M12 of T and apply it, and this sends it to, sends the basis elements to, let's see, oh, well, we've done this before, E2 plus TE1 plus E3, and E1 is left alone. But, oh, of course, this is, you know, we've got the V1 here. We can get rid of this TE1. So this is just equal to E2 plus E3, E1, and that converges to itself in the limit. So even though something happens on this basis element, nothing happens to the two-dimensional vector space. Okay, but if we didn't have that, if we just changed that a little bit, we'd get some interesting behavior. So let's consider the vector space generated by E2 plus E3 and E1 plus E3. So M12 applied to this gives you, well, the same thing happens in the first coordinate, E2 plus TE1 plus E3. And in the second coordinate, well, we still don't have an E2, so we're still fixed. So we get just E1 plus E3. But now we can't row reduce helpfully. And this now will converge as T goes to infinity. Well, I mean, okay, divide through here by T to see these going to 0 and this being fixed. We'll get E1 comma E1 plus E3, or just E1 comma E3. Okay. There's a theorem, or I don't know if it's a lemma or a theorem of Knudsen, which characterizes this. The limit action of Mij of T as above sends V to, well, it either fixes it if, let's see, if EI is in V, or V doesn't involve an EJ. or it sends it to V intersect E1 through missing EJ up to EN plus EI. Okay, so in the last few minutes, I get to tell you what I did. And that is to note that this these matrices act on the variety of vector subspaces of lambda k Cn. And the setup is completely similar. And I'm just going to go straight to the example here. Let's say I've got E2 wedge, E3, and E1 wedge, E3. So I guess I'm doing sort of the same example as before, but instead of taking sums in a vector space, I'm taking wedge products in an exterior algebra. So M1T, 1, 2 of T sends to E2 wedge E3 plus TE1 wedge E3. Right, so I'm applying the action to E2, and then I'm just extending across the product. And I fix the second generator, and let's write that out. So this is E2 plus TE1, whole thing wedge E3. Okay, because this is a product, I have a distributive law here. Okay, and so this will converge to E1 wedge E3. Oh, wait. So now, as before, I can row reduce to get rid of this. So this will converge to E2 wedge E3 and E1 wedge E3. Now, if I do this on E1 wedge E2 and E2 wedge E3, then something similar happens. This goes under the action to, let's see, E1 wedge E2 plus 0. So E2 goes to E2 plus something times E1, but E1 wedge E1 is 0. So I'm doing a little bit of algebra there. And then this gets sent to E2 wedge E3 plus T times E1 wedge E3. The same calculation is over here. Now, as T goes to infinity, this goes to E1 wedge E2 and E1 wedge E3, where I'm skipping the step where I divide both of these by T again. Okay, so I can always keep renormalizing. There, I put it in. Okay, So one theorem here is that if I have a set system, let's say a set system of k element subsets, and VA is the corresponding subspace of lambda k Cn as above, where this is corresponding to 1, 2, and 2, 3, set system 1, 2, 2, 3. Then this, the limit of this matrix action realizes the combinatorial shift in the sense that if I take the limit as t goes to infinity of my VA acted on by Mij of t, that's the same thing as the vector space corresponding to Sij of A. Okay, I'll mention, but I think maybe, well, I can give the details on request, but there's a description of this limit in general. And it's not so complicated, and it's a generalization of this combinatorial shift idea, but well, the details take a little bit of writing. So let me close here by going back for the to the questions that I wanted to ask. What's the relationship with combinatorial shifting in this Borel fixed-point approach? Well, these limits of matrix actions realize the combinatorial shifting. If I understand what the algebraic geometers and algebraic groups people do, and surely I do not, but if I understand a little bit of what they do, then the proof of the Burrell fixed-point theorem basically repeatedly applies things like these matrix shifting type operators. So I think this is a pretty good answer to this. I worked some on this question. So a game plan for it is to take the proof of this, which uses combinatorial shifting. The idea is you start with something which doesn't have the nice form, and you repeatedly combinatorially shift it until it does have the nice form, and then you try to look at what happens when it passes from one form to the other. There were some technical difficulties in trying to generalize that straightforwardly to the vector space system. So the system where instead of just having sets, I have what you could think of as being linear combinations of sets. Instead of just having monomials, I have linear combinations of monomials. And that's still an open question. Perhaps an enterprising student will go and solve it. Nothing would make me happier. And that's about all I have to say here. Are there any questions?
Thank you, Russ. Yeah, so it's time for questions and suggestions. So just go ahead, please. Anybody in Velika Predavalnica wants to ask a question, Blas?
No questions.
Okay, thank you. So if there are no further questions, suggestions, so thank you for joining us today. So next week, we will have a guest from University of Leeds. Isolde Adler will be with us via Zoom, of course. So you are all invited to join us next week at the same day at the same time. Okay. Bye, and Russ, thank you once again.
Thank you.
Thank you. Ciao.